Hello everyone, welcome back. In this video, I want to show you how to do lasso regressions in Python. And as with my earlier videos, I'm going to use the JupyterLab for this. Of course, if you are using Anaconda, you can use Spider for the same thing. Okay. And the data set that I will use for this video is here. It contains the information of the sale price of the house, or maybe I should open this one and let me put it here. uh, why I cannot wait. uh, it contains the information about the sale price of the house, and we want to find a relationship between the price of the house and the characteristic of the house, such as the size of the property. And also, before I continue, I want to emphasize that this dataset is not original. What I mean is that uh, it contains these interaction terms which are not the original variables, and also these ln cell and ln lot are the additional terms we created from cell and lot to correct for the the not so good model that we got when we were doing the regression with just cell and lot. Okay, so keep that in mind. When I read the data, how we want to drop the cell and lot. Okay, and what will happen is that this ln cell will be the dependent variable, and the rest will become the explanatory variables. Okay, with that, let's begin uh, writing the code. So the first step is always importation of the libraries. So I'm going to import Panda and stats models.api as sm. Okay. Oh, what did I? Oh, oh, yeah, I didn't put that. Sorry. With importation, then let's read the data. So we will be pt.read csv and housing sale price dot csv and header equal to 0, index column equal to 0. And I want to create a new data frame from the TF, because I want to drop the columns which are the cell column and also lot column. With that, uh, the let's look at the DFR. So you see, the first column is the dependent variable, and all these other will be explanatory variables. And what about the shape, the data frame? We have 546 rows and 22 columns, so 21 explanatory terms. So now I can do the regressions. Before I do the lasso regression, what I want to do is I will do the non-regularized regression, OLS regressions, and then we will do the lasso regression. The reason is that I want to see how much predictive power is reduced. How much predictive power is reduced by the use of lasso regressions. Okay, so instead of using all these 546 data points, what I'm going to do is I'm going to use only the 400 data points, and with the model I obtained from 400 data points, I want to apply the model to predict the values of the remaining 146 observations, um, and then calculate, and measure like mean absolute error. So let's begin the regressions. I need OLS, and my dependent variables are going to be dfr.ilog. I don't want the last 146 rows, so I do this in Python, just say minus 146, And my dependent variable, the row is the first row. And my second column is here. It will be the same, minus 146. And the columns will be 1 all the way down and all the way to the right. Sorry. And I will do fit. With that, I can also print the summary. Okay, that's good. But the summary is not really what I'm interested. What I'm interested is with the model I have now, I want to predict the values uh for the other 146 data. So I'm going to predict using this OLS 400, and my exogenous variables are going to be the explanatory variables, which is the same. Uh, but instead of minus 146, what I want is the 400 all the way down, which means that I don't want the first 400. I think this is fine already. So these are the predicted values for the observation from 401 to 546. Now I want to compare that to the original data. So, oops, sorry, it should be 0 here. So you can see a little bit of difference here. Like for 401, you see 11.5253, but for this one, the actual one is 11.43. So I want to calculate the predictive power of this model, and you know that we can use the one RMSE or MSE. So, but here, sorry, MAE. So here I'm going to use MAE, mean absolute error. So to do that, I will take the absolute of this one minus the real values, and I'm going to take the sum of it and divide by I know it's 146, so let's just say 146, and my MAE is 0.15, which is pretty good. But you know the main thing about Lasso is that when you have too many explanatory terms, you want to shrink it to only important terms. This is where the Lasso regression come in. And to do that, it is not really very much different. I just copied this one again, and here I'm going to put, say, Lasso, and instead of I'm training that I'm using the same 400, the first 400 observations, but instead of fit, I will need the fit regularize. And how do I know that? I mean, I have shown it before. If you come to this page, we used fit before, but now we are going to use fit regularize. And these are the input that we need to put in. And what is interesting here is that if you read the document, you will see that you can do a combination of L1 and L2 regression, with L1 being the Lasso regression and L2 corresponding to rich regression. So you can like do a bit of both here, but we're not going to do that. We were keeping things simple here, so we are going to use the Lasso regressions. And so the arguments for that are elastic net, and I think I need alpha, which is 0. I'm going to put it at 0.001. As we know, when alpha is huge, we are underfitting. When alpha is large, or we are maybe overfitting. And another one I need is, yeah, L1 weight. So I need to put it to 1.0 to specify that I'm doing Lasso regressions. And one more argument that I like to put in is here, which is zero tolerance, which shows that if the coefficients are below this zero tolerance, that coefficient will be treated as 0, which is cool. So let's put it there. I'm going to put it as zero tolerance 0.001. Okay, so this is Lasso regressions. But the only problem with the regularized regression for using this library is that as of now, I don't know why, but I cannot print out the summary if I do the fit regularized regressions. So I cannot print out the summary, but I can still retrieve the value of the coefficients. Okay, so to do that, it is not very difficult. Sorry, it should be equal to 400 lasso dot PIMS and 0 coefficients equal to lasso dot I think it's filter values, and I want to print this out coefficients. Oh, sorry. Yeah, so you see, uh, some of these terms have been reduced to 0. So I'm not going to use all the 21 explanatory terms, only some of it. And just now I said about if we increase the alpha, it will be under 15 because there will be only like one or two explanatory variables. Okay, let's look at that, if it is true or not. So when I increase the alpha to 1, we see that only two variables matter. The rest have been reduced to 0, okay, but which is not really realistic. So let's find the middle ground and let's use like 0.001, and then you have like 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11 explanatory terms out of 21, so which is pretty good. Okay, and with that, what I want to do is I want to find the MAE for the same uh, uh, for the lasso regressions, and I want to see how much MAE increase when we use lasso regressions. Okay, so I'm going to copy this and put it here, and instead of OLS 400, I'm going to use 400 lasso and predict all these are the same. Yeah, and let's see. So we get 0.35. Okay, so it is it increase, but it's not really big increase, I would say. And uh, although we drop like 10 explanatory terms, the model is still pretty good at predicting. Okay, so that's it for today, for this video. And later on, okay, for this video, as I said at the beginning, this data set is not really suitable for demonstrating the use lasso regressions, and because OLS already has a very good predictive power. I didn't even standardize the variables for lasso regressions here. But later on, I will be uploading a longer and more complicated video on both lasso and ridge regressions. Uh, so yeah, but for this video, this is enough, and thank you for watching and see you next time. Bye bye.